Okay, question 7. We've got a bit of Hooke's law here, and I don't know if it's going to ask us about elastic potential energy. I don't think it does. So the spring constant, so we know that's K. I'll get this ready now. Kentucky, oh, that K is terrible. Kentucky Fried X-rays. It says, calculate the force needed to compress the spring by the amount shown. So 6.2 millimeters. So we're going to have to divide that by 1,000 because we want it in meters. And it says calculate the force, so F equals K times X. It gives us K there. This is the spring constant K, which I've already written down. And then I've got that, but I've changed it to meters. So F equals KX, my 260 from my spring constant, multiplied by 0.0062, that's from my dividing by 1,000, equals 1.6. And it says give it to an appropriate number of significant figures. Well, 1.6 is a pretty small force. If I start going to more significant figures, if we now think of using the Newton meter, we've got, say, 1 to 5 newtons is some of the smallest ones we have. I think we've even got ones that might go to 1 Newton, but we don't have anything that goes to 2 decimal places. So it's just trying to think of what practical equipment in a school would we have to measure it. So the answer is 1.6 newtons. Okay, next one. The student removes the spring and they're going to investigate the compression. So we can see they're going to start here, then they're going to squash it down, measuring that force. And they're measuring the force on a balance, which is kind of clever actually. So they're going to press down on the force to change its length. They've got a lovely electronic balance that measures in newtons. We could just do the maths and times it by 10 if we wanted that for its weight, but here we go. So describe how the student can determine the change in the length of the spring. Well, clearly I would need to measure the length at the start. I need to measure the length at the end, and I need to subtract those two values. So read the position at the top of the spring against the ruler. If I wanted to, I could use a pointer, and I could attach a pointer to the start there because it just makes it easier for me to measure rather than lining it up. Read the position when it's compressed, subtract the two readings. It's a really easy question. This wasn't done particularly well by students, but it's the idea. Take the length at the start, take the length at the end, subtract the two. And I'd even draw on there to show what's going on. Right, so boom, 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 subtract those. Right, the student finds it difficult to make an accurate measurement of the change. Not a surprise, they're probably fingers in the way of reading the ruler. Describe one way they could improve it. Oh, I've done one already. But the one that came up in a previous paper is, well, I could put a set square there to make sure that's at 90 degrees to the surface. Or the other one is add a pointer to the top of the spring so I can read it more precisely. So use a set square, use a pointer, clamp the ruler, anything like this, ensuring that head is level. I think clamping the ruler is probably a bad one. It was in the mark scheme because the pan's going to move down a little bit, but use a set square or add a pointer onto the top of the spring. Or another one that was in there, make sure your head is level to give an accurate reading and avoid parallax error. Okay, so now we've got a spring hanging from a hook and we've got a force applying down, and it says the weight of the spring is 1 Newton. The weight of the block is 5 newtons, so I'll put the 1 Newton there. It says, therefore, the force exerted on the top of the spring is 6 newtons, but up. So it's exerted on the top of the spring. The crucial part is by the hook. So these are pulling this way, and the hook must be pulling up 6 newtons. And if this isn't moving, those forces are now balanced. Okay. Next part. Figure 9 shows two forces P and Q, so we've got a vector diagram. As we know, we never draw vectors bum to bum. So I'm going to move that line down, making sure I measure it, and we then know that would be the resultant force. So there's my arrow. And that's it.